Let's consider a fairly straightforward example that makes use of constant angular acceleration. So if you'll forgive me, let me write something out here. If an object with initial angular velocity (20 degrees per second) accelerates for 18 seconds, let's see, undergoes, this might be better, an angular acceleration of 2 degrees per second squared for 18 seconds. Then find the final angular velocity. Well, it may be straightforward, but a picture can still be helpful. So let's suppose that we have some sort of object, has an axis of rotation, and it's spinning around at 20 degrees per second. And that's going to be the omega initial. And I've chosen it to spin around in the counterclockwise direction, so the omega initial is going to be positive 20 degrees per second. And it's also undergoing an angular acceleration of 2 degrees per second squared. Well, we can sneak that into the picture too. That's going to be a constant angular acceleration, so there's the alpha of 2 degrees per second squared, and it does this for 18 seconds. So I can even write that one down. T equals 18 seconds. And what we want to do is ultimately find the final angular velocity. So we're really asking the question, the omega final equals what? Well, here we have the omega initial that's known, the time that's known, the angular acceleration that's known. If we look at our list of constant angular acceleration equations, I think the simplest one to get us there is just going to be the omega final equals the omega initial plus alpha t. The omega initial is 20 plus the alpha is 2, the time is 18, works out to be about 56 degrees per second. So it is one of the simplest examples possible, but part of what I want to highlight there is the fact that we work this in degrees, and again, for the basic constant angular velocity or constant angular acceleration equations, it doesn't matter which angular measure unit you use. Degrees are good, revolutions are good, radians are good. Just have to be consistent in your use of them. You don't want to mix and match in some odd way. Nevertheless, this does provide a first example of a constant angular acceleration problem.